All right, so when we're trying to count things, the way something is expressed is going to have an effect on how we count them. It's also going to depend on how the question is asked a little bit. So in this example, it says, a shop has 7 types of pies and 10 types of ice cream. How many different choices are there for one dessert? Okay. So how many choices for pies do I have? 7. And how many choices for ice cream do I have? 10. So then how many total choices would I have? 17, right? So in this case, if I were to think of my pies as set A and my ice creams as set B, well, a couple of things we would notice is that A intersect B would be the empty set. So then the number of things in A union B would be equal to the number of things in A plus the number of things in B, which was just 7 plus 10, which equals 17. So in this case, we had 2 disjoint sets, and we were asked to pick one thing from either of those 2 sets, right? We were asked to pick either a pie or an ice cream, but not both, right? So we were to pick one dessert, and we made the set of all desserts by unioning the 2 sets together and then picking one thing out of that set. So this is an example of what's called the addition principle. So if my 2 sets are unions together, and then I'm picking things out of that new union set, our total number of choices is the number of things in the union, assuming that the sets were disjoint to begin with, right? And ice cream and pies were disjoint, so we didn't have to subtract off anything in our intersection.
So what if you only multiply the 2?
We'll get to that in a second. So this was an example of what is called the addition principle. So basically, when the following happens, when choosing among our disjoint alternatives, so first thing we notice is that they have to be disjoint. Suppose that alternative 1 has n possible outcomes, alternative 2 has n2 possible outcomes, and alternative r has n sub r possible outcomes. And with no 2 of the outcomes the same, then the total possible number of outcomes is n1 plus n2 plus all the way out to nr, which is like what we saw here. These things were disjoint. We had 7 pies, 10 ice creams. If we had to pick one thing out of all of them, there were a total of 17 possible choices, right? So now let's look at this previous example, but in a different way. So we're going to change the way we think about it. So now at this same dessert shop, if the pies are sold a la mode with 1 scoop of ice cream, how many choices are there for one dessert? Well, so we still have the same number of pies. So we know that there are 7 choices for pie, and we know that there are 10 choices for ice cream. So now, how many different desserts are possible using this configuration? Well, it's not going to be 17 anymore, right? So, because what are we doing now? So how many choices do you have for a pie? 7. And then each type of pie is paired with what? 1 scoop of ice cream. So if you look at it like this, for each pie, so if I call this pie 1, so if I select the first pie, then to get to the next step, I have 10 choices, right? Because there's 1, 2, 3, 4, 5, 6, 7, I'm running out of dashes, 8, 9, 10, right? So for each pie, it gets paired with possibly 10 different flavors of ice cream. But then for how many pies do I have to do that? For 7. So each pie can get paired with 10 ice creams times 7 times. How many possible combinations are there? 70. So in this case, it is an example of what is called the multiplication principle. And a good way to think about this, in my first stage, so stage 1, what do I pick? Well, my first stage is I pick my pie. How many choices do I have? 7. Then in stage 2, I pick my ice cream. And how many choices do I have? 10. So in terms of my ordered pairs of pie and ice cream, for the first coordinate, I have 7 choices. And for the second coordinate, I have 10 choices. So then this is going to be 70. Well, this is exactly the same as the number of things in A cross B, right? Which is the number of things in A times the number of things in B. So the difference here between this and the first example is instead of picking one thing out of all of the possible items we were talking about, which is the union, we're now creating ordered pairs where we're picking something at each stage in a multi-step process, right? So like if I was at this restaurant ordering dessert, I would have to tell the person or my server what pie I wanted. Second step, I would have to tell them what ice cream I wanted, right? So I made 2 choices, stage 1 and stage 2. That's what tells us that this is a cross of the 2 sets. So we are going to multiply the size or the cardinality in each stage together, right? Because we're creating different desserts by pairing a pie with an ice cream. So they're ordered pairs as opposed to picking a single object. All right. I know that that's not perfectly clear yet, so we'll do a little bit more, have you guys work on one. So basically, to summarize what we just said is the following. So this is the multiplication principle. When making a sequence of choices with our steps, suppose that step 1 has n1 possible outcomes, step 2 has n2 possible outcomes, and step r has n sub r possible outcomes. Then and that each sequence of choices results in a distinct outcome. Then there are a total of n1 times n2 times ... all the way out to nr possible outcomes. So if we have a multi-step process where we have to make a choice at each step, the total possible number of outcomes is the product of all of our possible choices at each step. So in the previous example, we had to pick our pie, then we had to pick our ice cream, and we multiplied them together. All right, so here is your you try. At a sandwich shop, there are 7 types of bread, 10 types of meat, and 6 types of cheese. How many choices are there for a meat and cheese sandwich? So go ahead and see if you can calculate how many different possible sandwiches can be made from 7 types of bread, 10 types of meat, and 6 types of cheese. All right, so we're going to be making a sandwich, and our ordered triples in this case are going to look like bread and meat and cheese. So then it's going to be the number of choices of bread times the number of choices of meat times the number of choices of cheese. So we're going to have 7 times 10 times 6. So 7 times 10 is 70. 7 times 6 is 42 with a 0. So it would be possible to make 420 different types of sandwich from 7 types of bread, 10 types of meat, and 6 types of cheese. All right. So the multiplication principle is when we're combining all of these things to make one item, aka a sandwich, but we have choices at each step in our process. All right, let's keep going. So our next example reads as follows. You walk into an ice cream parlor and find that you can choose between ice cream, of which there are 15 flavors, and frozen yogurt, of which there are 5 flavors. In addition, you can choose among 3 different sizes of cones for your ice cream or 2 different sizes of cups for your yogurt. If you only want a single item, how many different desserts can you choose from? Okay. So we have 2 stages, right? Because what's the first thing that we need to pick in this process? Okay, so there's a couple of different ways that we can look at this. So when we walk in, we have our very, very first choice, which is what? Ice cream or frozen yogurt. And then what's the next thing we have to pick? Flavor. And then we have to pick a size, right? So when we walk in then, we can look at it as follows. So we're going to pick the type is what I'm going to put it. So it's either ice cream or frozen yogurt. And then what's our next choice? Flavor. And then what's our next choice? Size. But here, that's going to cause a little bit of a problem because we'll see why when we try to work it out this way. There's a way that it'll work, but we're going to talk about a different way to help us out here. Because if we try to do this, we pick our type, right? So we would have 2 choices. But then, now how many choices do we have for flavors?
There's 15 for ice cream for 15 and 5 for frozen.
Yeah, so we want to say 15, but now we've got a little bit of a problem because we're trying to use the addition principle. And our stuff's not going to be disjoint quite yet. So we need to back up a little bit and think of this in a different way, and we'll draw a picture to help illustrate this idea. So we've got to be a little careful when it comes to counting because it's very easy to miscount. So let's just make it a little bit simpler when we do this. We want to pick a flavor and we want to pick a size. So to help illustrate what's happening, let's break this up into 2 different things for a minute. So what if we just wanted to focus on ice cream for a minute? So let's look at each of them separately. So if we focus on the ice cream, how many choices for flavor do we have? We have 15 times. Then how many different sizes do we have? 3. So how many different ice creams can we make? 45, right? Because we have 15 flavors and 3 sizes, so there are 45 different ways that we can do ice cream. Okay. So then now, what do we need to do next? Yeah, so let's try frozen yogurt. So with frozen yogurt, we're now going to pick, well, how many choices of flavor do we have? 5 times how many different sizes do we have available? 2. So we have 10. So then we're going to notice that these two things are disjoint. Right? They share no elements in common. So each of these were calculated using the multiplication principle. But since they're disjoint, then the total number of choices is, well, it's going to be the union. So we're going to add using the addition principle. So then the total number of choices would be 45 plus 10, which is 55.
So what is the how many options you have?
All right, so let's take a look at our U-try. So we have 2 types of cake, German chocolate and strawberry. And we have 3 pies, apple, banana cream, and rhubarb. And then we have our choice of vanilla and chocolate ice cream. And the manager's special is a piece of cake or a slice of pie and 1 scoop of ice cream. How many different specials are there? Well, let's break this down into 2 different things to get started. So let's start with cakes. So if we start with our cakes, how many choices do we have? 2. And then cakes to ice cream, how many different choices do we have for ice cream? Also 2. So that means there's going to be 4 choices with cakes. And if we go with pies to ice cream, we have 3 different types of pies and 2 different types of ice cream. That's going to give us 6. So there's a total of 4 plus 6, which is 10 specials. So if we had a special consisting of one piece of cake or 1 slice of pie and 1 scoop of ice cream, there would be 10 different possible desserts for someone to order from, right, on that specials list. So this leads into the idea of a decision tree. So in this case, a decision tree is going to help us visualize what's happening. So in terms of what we have going on here, so our first choice is going to be between cake and pie, right? So if we have cake, we're going to go up. I might need to move that down. I'm going to need a little more space. And if we have pie, I'm going to represent that by choosing to go down. So if I do this in my decision tree, how many cakes did I have to choose from? 2. And how many pies did I have to choose from? 3. So then, now at my cake node over here, after I picked my cake or pie, I'm now going to pick ice cream. And how many ice creams did I have to choose from? 2, right? So I'm getting ahead of myself. So I make one choice here. I pick either cake or I pick pie. And then with cakes, I had 2 choices. So I'm putting... Sorry. I'm getting ahead of myself. Let me change my nodes. Instead of putting the stuff here, I'm going to put them here. We'll do the number nodes later. So I'm going to do cake in my node. And I'm going to do pie in my node. So then, after I choose cake or pie, I need to pick which type of cake. So what were my choices for cake? German chocolate or strawberry shortcake, right? So that's my node here, and I'm going to do strawberry. And that's here. Then I do the same thing for pies. I have 3 possible choices this time. And for pies, I had apple, I had banana, cream, or rhubarb. So then finally, at the very, very end, I have to pick a type of ice cream, right? So vanilla or chocolate. And I have to do that for each of these. So I made this decision tree, and if I were now to count all of the things at the very, very end, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What does this tree represent? The total number of options that I had. And if I look at my tree, it's 1. Here I had 1 choice. Here I had 2 choices. So sorry, at my node 1. And then here I had 2 choices, and then here I had some more choices. So we're getting that it breaks it up, and basically, if I followed my tree all the way to the end, it's telling me I picked cake, German chocolate, and vanilla. That would be one of my ordered triples, right? That would represent that situation. So we can always enumerate our number of choices by creating a decision tree. But how many things did we have to work with this time? Just 2 cakes, 3 pies, and 2 ice creams. And this tree got really ugly and really kind of spread out very quickly, right? So while decision trees are very, very helpful for helping us visualize things, oftentimes actually creating them is not going to be very useful. We can create an abridged version of this tree by putting just the number of choices that happened in each step. Well, we had to choose from either cake or pie, which was 1. And then from cakes, we had 2. And then from these, we would have 2. So this one would go 1, 2, 2. And this one went 1, 3, 2. And if we multiply out, we get 4 and 6, which gives us our total number of choices. So it's not the best way to do things, but it can still help us visualize what's going on. When we have straight multiplication principle, we're moving along a line. In some of these cases where we have different possibilities, we get branching, which makes it so we have to mix both the addition rule and the multiplication rule. So we need to be cognizant, and these trees can help us visualize some of those things a little bit better. All right, so now let's take a look at our next example. Using the letters C, A, and T, how many three-letter words can be made? So notice the word words is in quotes because not every arrangement of C, A, and T is going to produce a word, right? So, well, let's see. How can we do this? Well, I guess we could always do a brute force approach. Let's see. So one arrangement we know is CAT. Another arrangement would be CTA. And another arrangement would be TCA. Another arrangement would be TAC. And then another arrangement would be ACT. Let's see, are there any other ones that we haven't done? What about ATC? Good. All right. So are there any that I've missed so far? So I think that's all of them. So how many three-letter words were we able to make using three distinct letters? 6.
Combinations, or do you mean like words?
No, so just combination. That's why we put words in quotes.
Okay.
So it's any rearrangement of the letters.
Okay.
So the words don't have meaning in the sense of words. So there are 6 of these that we were able to make. Okay. Let's think on this again. So now what if we started with this group of letters? So using the letters M, A, D, and D, how many 4-letter words can be made?
So it's just the one is repeating itself.
Yeah, so we have 4-letter words, but we have D twice. Okay, let's see. Let's go back to example 4 for a second before we talk about example 5. So why did we get 6?
That's how many outcomes there are using those two different.
Right, so if we come back and we look at a comparison to some of our previous things, if we're making a 3-letter word, how many choices are we making? Well, what do we choose? How many stages are there? What do we have to pick? The first letter, and then what do you have to pick? The second letter, and then what do you have to pick? The third letter. Okay, so using that type of stuff in stage 1, if I have CAT, how many letters do I have to choose from? 3. Then I've picked one, so now how many letters do I have left to pick in stage 2? 2. And then in stage 1, or our last stage, stage 3, how many letters do I have left to pick from? 1. So I had 3 choices in stage 1, 2 choices in stage 2, and 1 choice in stage 3. So 3 times 2 times 1 equals 6. Okay. So based on that, now we want to know, well, how many 4-letter words can be made using M, A, D, and D? Well, let's see. Using that same logic, how many choices do we have for our first letter? 4. How many choices do we have for our second letter? 3. How many choices for our third letter? 2. And how many for our last letter? 1. So 4 times 3 times 2 times 1 would be 24. So unfortunately, that's not quite right. And let's see why. So what if I were to just write them down in order? So I had M, A, D, D. The problem is, can I tell the D's apart? No, the D's are indistinguishable. So when I'm making my choices, the way I'm counting them, it is as if I can tell them apart, because that would be one possible arrangement. Another possible arrangement would be to put the purple D first and the blue D second. But since we don't really have color-coded Ds, can I tell MADD from MADD if I don't have color? No. So when I have my choices and I count 4 times 3 times 2 times 1, this is assuming that all of them are distinguishable. So this assumes all objects are distinguishable. But they're not, right? So we can't tell the D's apart. So now we're going to have to figure something out. All right, so let's make some assumptions and see if we can figure this out. Well, if we can't tell the D's apart, then things that look like MADD and MADD are indistinguishable, right? So the same thing would be true if I had DMAD and DMAD. Well, what does that seem to show? So since we have 2 D's, what's going to happen to each one of these things? How many ways can we do this? 2. So no matter where the 2 D's are, I could rearrange them as ADMA and ADMD and ADMD. There we go. And I'm always going to have 2 pairs of them that, unless I can distinguish the D's from each other by color coding them, I can't tell these 2 things apart. So 24 is going to count everything how many times? Twice. So everything, every group is counted twice. So then 24 if every group is counted twice, then 24 divided by 2 gives us 12. So that would mean there were 12 pairs of 2, right? And if we can't tell those two things apart, then there is only 12 words that can be made, right? Because MADD is the same as MADD regardless of which D is put first.
So what would it mean if you multiply the 24 times the 2?
Let's see if we can figure out a pattern. So how would this change now if we had 3 Ds? Well, how many things would be in each group? So let's look at a simpler example. What if I had M, D, D, and D? Okay, we still have 4 letters, so we might think that there's going to be 24 choices, but we know that's wrong, right? That's if we could tell them all apart. Well, how many different things could I make out of M, D, D, D? Well, my letters would be M, D, 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 M, D, 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 M, D, and D, 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 M. Those would be the only 4 I could tell apart. So how many ways could I rearrange this? Only 4. Well, let's think about it. So my M has to go somewhere, right? But then my D's, how many ways can they be rearranged? Well, if I think about it by color coding them to give me some perspective, if I have 3 things that I can tell apart, how many ways can I rearrange them? Well, how many choices would I have for my first D? Well, if I could pick from green, purple, and blue, I would have 3 choices. So I pick one, then how many would I have for my second D? 2, and then my last D would be fixed. So how many different ways can I rearrange 3 Ds? 6. So in each of these things, how many rearrangements of D would there be? 6. Because I would have 6 choices if I could distinguish them. So that means I am overcounting by, each group has 6. I have 4 groups of 6, so I divide by 6 and I get 4. So notice we divided by the number of things that was repeated counting down, just like we did up here. So up here I had 24 divided by 2 because this was 4 times 3 times 2 times 1. So this is how many choices we have for 4-letter words. And then divided by 2 times 1, ways to arrange the repeats. So the D's, 2 D's, can be rearranged. Was 2 times 1, right? So using that same thing here, we would still have 24, which was, we had 4 choices, 3 choices, 2 choices, and 1 choice, but then we had 3 times 2 times 1, and we get 4, right? So if we have things that are indistinguishable, to correct our counting, we need to divide by the number of ways that we could rearrange those in each step, right? So we're combining our multiplication rule with this idea to get rid of this overcount, right? When we have things that are repeated. All right, so how many 3-letter words could be made using food? Well, if we did this, we would have the following, and let's use this to write out with decision trees all of the possibilities. So I gave us the tree because they're really I don't want you to have to draw them, and they're hard to draw by hand. So let's go ahead and list all of the possibilities. So if we were trying to do all of the possibilities, our first letter could be F, our second letter could be O, our third letter could be O, and our fourth letter could be D. So then if I did my next thing in each of these, so filling out this first bracket, I've already used the F, so what are my things that are left? O, O, and D. So then my choice here is I could put an O here, and a D here. And if I did that, I've used one O and an F already. So then I'd have an O and a D left. And then this one would have a D, and then that would have an O. So similarly, I've used an F and an O. So this one's going to do the same thing, O, D, and then it's going to be D, O. This one I'm going to have O, O, and then O, O. So then, what would be the possible words that were created here? So I would have food, I would have F-O-D-O, I would have food again, and then I would have F-O-D-O again, and here I would have F-D-O-O and F-D-O-O. So we notice when I did this, I get a whole bunch of them that repeat, right? So I have food and food, photo and photo, and here. So out of those arrangements, it shows all of our things that paired up. That's what I was talking about, right? And if we list the same thing here, our next phase, we would have an F, we would have an O, and we'd have a D. So then here, after we picked O and F, we would have an O and a D left. So then that would be D and an O. Here we would have an F and a D left. So then we would have D, F, and here we would have an F and an O left. So then that would be O and F. So here we would get O, F, O, D. Here we would get O, F, D, O. Here we would get O, O, F, D. And here we would get O, O, D, F. And here we would get O, D, F, O, and O, D, O, F. So here, does it look like we ended up with anything that repeated this time? All right, so we go to our next one. So we have our O, so then we would have an O left, we would have an F left, and we would have a D left. So if we go up here after O, we would have F and a D, and we'd have a D and an F. Here, O, F, we'd have an O and a D, and then we'd have a D and an O. O, D, we'd have an O and an F, so then an F and an O. So then we have OOFD, OODF, we have OFOD, and OFDO, and then ODOF, and ODFO. Oh, wait a minute. Where have we seen all of these before? Oh, they're exactly... Some of them are exactly here. So we have OOFD. So OOFD, OOFD. We have OODF. That's here, OODF. That's here. And then we have OF, OD, OFOD, oh, that's these ones, and OFDO, that's here and here. And then, sorry, I shouldn't be, I only should be doing that in one of them. And then lastly, these also pair with over here, ODOF. Okay, so did it again. These ones. So in fact, these two worked out to be exactly the same thing again, right? So that one gave us no new choices. And then finally here we have our D. So then I would have O, O, and F. Here if I used one O, I would have an O and an F left. And then here I'd have an F and an O. D, O. So I'd have an O and an F, and an F and an O. And D and an F, I'd have an O and an O and an O and an O. So then I would have D-O-O-F, D-O-F-O, D-O-O-F, D-O-F-O, and then D-F-O-O, and D-F-O-O. So once again, a whole bunch of things are going to be the same, right? So D-O-O-F, and D-O-O-F, D-O-F-O, D-O-F-O, D-F-O-O, and D-F-O-O. So then finally, we count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is exactly the same thing, right? So we can make our decision trees to help us do this, but that's going to be really, really long. Because as we surmised up here, it's going to be, we have 4 letters, so that's going to be 4 times 3 times 2 times 1, divided by the ones we can't tell apart, which is 2 times 1. They reduce out, and we get 12, right? All right. So let's take a look at sample number 7. So determine the number of possible passwords of length 8 if A, only lowercase letters are used. So how many letters are there in the alphabet? 26, right? So if we only use only lowercase letters, and we're going to make a password of length 8, 1, 2, 3, 4, 5, 6, 7, 8. So if I use only lowercase letters, how many choices do I have for the first thing in my password? 26. And then how many choices would I have for the second thing in my password? Well, it doesn't say they can't repeat. So you'd still have 26 choices, right? Because there's 26 letters in the alphabet, right? I wouldn't recommend having the password A, but it is a possibility, right? It just said how many are there. So then for the third letter, what could you have? 26, 26, 26. In fact, for all 8 of them, how many choices do you have? 26. So that would be 26 to the 8th power. And what is 26 raised to the 8th power? So we get 2.08 and some stuff. And what does that E11 mean on my calculator? Well, that is my calculator's way of telling me about scientific notation. So that means how many places to the right do I need to move my decimal? 11, right? So this e to the 11th means times 10 to the 11th power. So 9 places to the right would be our billions column. So this is going to be like 208 billion possible passwords. I know that seems pretty big, but how many computations can a computer do in a second? Well, a gigahertz, what does giga stand for? So let's see. We have kilo is 1,000, mega is 1,000,000, and giga is a billion. So if we have a processor that's measuring things in gigahertz, that means it can do that many billions of additions per second. Then you have to multiply that by cores and threads, just to give us an approximate idea. So using the most inefficient process possible, a computer could guess all 8 character passwords using only lowercase letters in less than 200 seconds. It's actually much less than that. It's a fraction of a second because of multi-processing. Just to give you the idea. So that's why they don't like you to make passwords using only lowercase letters. So part B. How would this change if we used upper and lowercase letters? Well, if we use upper and lowercase, that means instead of 26, how many choices are we going to have? Well, it's going to be twice as many, right? Because you're going to have big A and little a, big B and little b, big C and little c. So instead of 26, we would have 52. But if I do that for each of my 8 things, what am I going to end up with? 52 times itself 8 times. So I would get 52 raised to the 8th power, which, okay, well, instead of 200 billion, what do we end up with? 500 billion. Okay. Well, it's a little better. But nowadays, do they let you have a password that only contains letters in it? No. What do they make you put in your passwords now?
Numbers.
We got to have a number. Okay. So part C says, what if we use the upper and lowercase letters and the digits 0 through 9? So how many choices will we have at each stage now? Well, we'll have the same 52 that we already had. Using the addition principle, we're adding 0 through 9 as possible choices, so that's 10 more. So by the addition principle, it would be 62, right? 52 plus 10 is 62. And then we would have 62 choices how many times? 8. So we'd have 62 to the 8th power. So if we grab our calculator now and we do 62 to the 8th power, okay, so now we're up to e to the 14th. So now we're at 2 trillion of them. So our number keeps getting bigger. But then what do they start doing? Well, adding numbers isn't good enough. So then they're going to add a couple of special characters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I thought I did 10 of these too. Apparently I only did 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So now by the addition principle, 62 plus 9 is going to give us 71. And we're going to have 8 of those once again. So 71 times 8. So, or 71 to the 8. So 71 to the 8th power gives us 6 trillion possibilities, right? So this is why they keep creating these terrible, terrible password requirements, is they're trying to make them longer and longer. But this is also why now people, instead of saying, oh, instead of making them 8, do a password sentence. So make it 30 characters long, right? So then you would have to multiply all of these things together that many times, and it just keeps getting ridiculous. So that changes our number of choices quite a bit. So this time we end up with 6 trillion possibilities. All right, you try number 3. So redo the previous example, but this time each letter, digit, or symbol has to be unique. So no repeats. So if you're only allowed to use each letter or symbol at most 1 times, redo the previous example and calculate that. All right. So for part A, if we're using only lowercase letters, our first choice would be 26, then we would have 25, then 24, then 23, then 22, then 21 times 20. I lose track. 3, 4, 5, 6, 7, and 8, so times 19. So then if we multiply all of those numbers together, we get 26 times 25 times 24 times 23 times 22 times 21 times 20 times 19, and we get the following number. So compared to our first example, instead of times 10 to the 11th, it's times 10 to the 10th, right? So it's a bit smaller than our previous one. Okay, so then for part B, we're going to have the same thing, but we do 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45. So 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45. And this time we get 10 to the 13th again. All right, so for part C, we've now added the digits 0 through 9, so that's going to be 62 times 61 times 60 times 59 times 58 times 57 times 56 times 55. 62 times 61 times 60 times 59 times 58 times 57 times 56 times 55. All right. And then lastly, for D, we had 71 choices to start. So 71 times 70 times 69 times 68 times 67 times 66. 1, 2, 3, 4, 5, 6 times 65 times 64. All right, so 71 times 70 times 69 times 68 times 67 times 66 times 65 times 64. Whew. Finally, we get this value. All right. So, a couple of things we want to mention. Seems like when we're choosing these, we're going to be multiplying a lot of things together when we have a multi-stage experiment. So we may wish to try to come up with a more efficient way to do some of these things. And that will be our goal moving forward from here.